Good evening, sir.
Hi Rucha, good evening.
Sir,
Good evening.
welcome to Vortex. Sir, welcome to
Thank you.
Vortex. Sir, welcome to Vortex. Sir, we'll be starting in a few minutes. Some of them are joining.
Okay. Okay.
Good evening, everybody. We'll be starting. Good evening. Welcome to the first lecture of Masterclass, a guest lecture series and one of the flagship events of Vortex. Masterclass provides us an opportunity to learn with the best, to interact, improve, stretch, and implement new innovative ideas in science, technology, and research. Today, we have the honor of having with us Professor Vivek Polshettiwar. He is a part of the Department of Chemical Sciences at Tata Institute of Fundamental Research, and his list of achievements is so long that we might have to take another lecture for that. He received an Asian Rising Star Lectureship at the 15th Asian Chemical Congress in Singapore 2013 from the Nobel laureate Professor Nigish. In 2015, he was admitted as a Fellow of the Royal Society of Chemistry, United Kingdoms. He was also awarded the Bronze Medal by the Chemical Research Society of India and the prestigious MRSI Medal 2019 and Fellow Maharashtra Academy of Sciences. In 2020, he received the Young Research Awards in Nanoscience and Technology by DST Government of India. In Jan 2021, he has been elected as a Fellow for the National Academy of Sciences, India. With more than 100 articles with H index of 54 and around 12,000 citations in reputed journals like PNAS, AgNewChem, and ACS Catalysis, sir, you are the epitome of inspiration. His recent publications include plasmonic collidosomes of black gold for solar energy harvesting and hotspot-directed catalysis for fuel conversions in 2019, and in 2020 it was defects in nanosilica catalytically convert CO2 to methane without any metal or ligand. His current research work includes designing and synthesizing various nanomaterials with specific shapes, sizes, and morphologies, and then evaluating their uses as catalysts for the development of sustainable protocols for various challenging processes like photocatalysis, CO2 capture and conversion to chemicals, environmental remediation, as well as carbon hydrogen activation, carbon carbon coupling, oxidation, and hydrogenation reaction. It also aims to develop novel nanomaterials as catalysts to tackle climate change. With this, I would like to welcome Professor Polshettiwar. We are delighted to have you here, sir. Chemistry can help us understand, protect, and improve the environment around us. Without any further ado, please welcome the first guest speaker for Masterclass series in Vortex, Professor Vivek Polshettiwar, on the topic Role of Chemists to Combat Climate Change.
Thank you, Komal, for a nice introduction, and thank you, Rucha and other organizer for inviting me for this for delivering the talk. So let me share the PowerPoint presentation. So, can you confirm that you are able to see my slides and able to hear me?
Yes, sir.
Okay. So, so today I'm going to talk about role of chemist, because this is a gathering of chemists, I guess, at the Institute of Chemical Technology.
Sir, I'm sorry to interrupt, but I would also like to introduce and tell you guys that Professor Prashant Kharar is also here. So a cheer for him too. Thank you.
Okay. Thank you. So, so today I'm going to speak about role of chemists to combat the climate change, which is a general title, and more technical title will be how do I capture and convert the CO2, which is in excess, which is the cause of the climate change, as well as the waste plastic to chemicals. That at the end of the talk, I will touch upon these two technical details. So the way I'm going to deliver the talk today is I'm going to talk about the climate change, which most of you already know, but I'm going to discuss a bit of chemistry of the climate change, and that will help us to really understand how the chemist can help in tackling the climate change. And then, so the chemist can help in a different ways. So one of the way is by developing a nanomaterial. So what is the role of a chemist to develop the nanomaterials and nanotechnology? In order to understand that, I'm going to explain what is nanoscience, nanotechnology, and then using some of the examples in our lab, I will try to explain how one can synthesize different kinds of nanomaterial, which will help us to combat the climate change. And if time permits, we'll touch upon waste plastic to chemicals. So what is climate change? I guess we all know, because of the excessive greenhouse gases, mainly CO2, there is a global warming, which causes the climate change. One can understand the climate change using this simple slide, which can be considered as Earth's energy budget, where we know we are getting the energy from the sun. So you get around 340.4 watt per centimeter square energy from the sun. Some of that energy get absorbed by the atmosphere. Large amount of that is received by the Earth, and several of that again get reflected. Some portion get reflected, some portion get absorbed, and that absorbs solar energy, then again re-emitted in the form of a thermal radiation. And the natural cycle is that you get the energy from the sun, some gets reflected, some get absorbed, some get again re-emitted, and that allows us to have this unique temperature that we have on planet Earth, which help us to have the life on planet Earth. But somehow the emitted radiation now getting trapped in the Earth's environment, and the reason for trapping those emitted radiation and some of the reflected radiation is because of the CO2 in the environment and other greenhouse gases. But CO2 is the main cause. That's why I keep referring to CO2. So more the CO2, more will be trapping up these emissions, secondary emissions, thermal emissions, and those will then again send it, that will get trapped into the environment, and environment will get heated, globe will get warmer, and that causes the global warming, which again impacts the climate on planet Earth. So these are the greenhouse gases. CO2 is the one. Why CO2 is critical? Because CO2 is a linear molecule, very stable. It has a very high lifetime. So nothing happened to it even in the environment. So that the impact of the CO2, the global warming impact of the CO2 on the planet is extremely high. Methane is another greenhouse gas, although the lifetime of
Vortex के वो नहीं बोला. I'm just all of the people. यो समीरा भी आपको दिखता है.
Can I request everyone to mute themselves? Can I request everyone to mute themselves? Okay. So then the another molecule is methane, which is also considered as around 20 times more harmful than CO2, but it has a lower lifetime and it can be used as a fuel. So you will see that in our work, we're trying to convert CO2 to methane, and that can also take care of the climate change problem, which looks not obvious, but I will try to explain that. Then nitrous oxide, even water vapors can be considered as greenhouse gases because they also absorb these, secondary emitted IR radiation. Although there is always a debate because water is the increase in the water vapor in the environment is because of the global warming. So it's some sort of a secondary effect. So if you somehow reduce the global warming, the water vapor effect will also go down. Why these gases are considered as the greenhouse gases? Because the outgoing radiation is in the form of infrared radiation in majority, and these radiation get absorbed by some specific molecule. You can see water, carbon dioxide, methane, nitrous oxide, and that traps those secondary radiation, that traps those thermal radiation, and that's why these are called the greenhouse gases. Now, what happens if there is a global warming? We know now around it's 400 ppm. I think it's 420 ppm now in this December. And you can see a dramatic increase in the CO2 concentration in the environment. Before industrialization and after industrialization, there is a dramatic change in the CO2 concentration. And because of this increase in the CO2 concentration, the average global temperature is also increasing every year. And one can say, oh, that increase could be due to the more and more solar energy coming from the sun. You can always have an argument if you don't want to believe in the climate change. But then there is this data which indicate that the amount of solar flux that we received is nearly the same within the error bar, whereas there is an systematic increase in the temperature, clearly indicating the global warming. So because of the global warming, what will happen? The first thing that will happen is the ice in Arctic Sea will melt. So you can see now in 1980, it was around 7 million kilometer square. And by 2015, 50% of that ice is melted already. So that's the huge area of the ice which is melted. Now, because of the global warming, And because of the melting of the ice, what will happen? The sea level will go up, right? Sea level will rise. And this is the data which clearly indicate that there is a systematic increase in the sea level. This is very recent work in Nature Communication. Obviously, it's a modeling, but it says that if we continue the way we are living, the way we are producing the CO2 and not doing anything with that CO2, at least in India, then very soon the Mumbai gateway of India will be in water. And you can imagine Mumbai would be one of the most affected city because we are just at the sea, and most of the other cities at the sea. So definitely, it's a very serious issue. We need to really worry about the climate change. It's not also about melting of the ice, global warming in terms of increasing the sea level, but it's also about the diseases. We are all now struggling with a coronavirus, COVID-19 specifically, but you know that before COVID-19, there were different coronavirus which were already there, already known to the scientists. And in fact, that helped us to come up with a vaccine and other treatment because we already had a knowledge about that virus, at least other virus of that class. But imagine a virus which is not known to us for millions of years, or a bacteria which is not known to us millions of years, and suddenly it come to our life, then we're not able to have anything. We're not able to tackle them because we don't know the structure, the shape, we don't know how they act, right? So, and that is what seems to be happening. In 2005 study, NASA scientists, revived the bacteria, which is 32,000 years old. In very recent 2017, they again found different kinds of microbes which are extremely old, and they found that these microbes are resistant to all the top 18 antibiotics that we know, right? So we can imagine such a serious impact on health, and in addition to the environment of our planet. So now, is it too late to stop the climate change, or can we do something to stop the climate change? So one can say this: life, the most complex form of a matter in the universe, is on course for its inevitable extinction. So we just must relax and wait until that happens, unless we humans, the chosen one, can agree to live within the limits of these rules of the nature, right? Minimize the use of energy, waste of the energy, creating the waste, throwing away everything, and that all produces the CO2. So definitely there is a need to change our lifestyle. There is a need to control the population on the planet, how we use the energy, which energy source we use, and how efficiently we use those energies. And in addition to that, what technology can do, what chemists can do to combat the climate change. So if one look at the climate change, the simple solution is somehow I capture the CO2 in the environment, or I capture the CO2 before it enters the environment. So CO2 capture is a simple solution. You capture the CO2, reduce the CO2 concentration from the environment, and done, right? That reduces the impact, the climate change. And if you can again convert that CO2 into some useful chemicals, say CO2 to methane or methanol or ethanol, then ideally you are using that waste CO2 to produce chemicals, to produce medicines, or to use them as a fuel, right? So CO2 becomes some sort of a carbon source rather than the waste. And that's what the trees does, right? Artificial photosynthesis is so trees does the photosynthesis where they take the CO2 from the environment, water, and the sunlight, and you get different products, food products. So can a chemist develop something which allows us to do the same thing that plants are doing? And that's why we call them artificial photosynthesis, where you capture the CO2. This is a typical nature lives, right? So you have energy coming from the sunlight, and then the plants and trees are doing the photosynthesis, taking the energy from sunlight, those photons, CO2 from the environment and the water, and you get a different products. Somehow we have now more industries, and our lifestyle is such that we produce large amount of CO2 that any number of trees that we plant, it will never able to take care of those CO2. Obviously, we should plant as many trees as we can, but there are several studies which clearly indicate that we cannot really plant the required number of trees because of the limited space, limitation of water, that the trees alone can take care of the excess CO2. So what you need is artificial trees, which will do the same thing, but these artificial trees will not need a land, which will not need a water, and still they will be able to capture the CO2, capture the sunlight, and limited amount of water to convert CO2 to say methane and methanol. So the how do I now design the artificial trees, and what is the role of a chemist to design the artificial trees? So artificial trees is again a fancy name. What what it really is, it's a material, some sort of material in the sense like let us say a sand on the beach. Can I so sand on the beach is a silica, right? SiO2. So can I do something with that sand which will which will capture the CO2, harvest the solar energy, split the water, and convert that CO2 into methane and other useful chemicals. So can I develop those type of nanomaterials by using the concept of chemical sciences? And so those are nothing but the artificial trees. Those are the nanomaterials, nanocatalysts, which behaves like a tree. I mean, another way of saying the same thing is this looks crazy, right? Can I drive a car by filling the CO2 in your petrol or a diesel tank, right? You don't put a petrol or a diesel or a CNG, but fill with the CO2, and make it even worse. You fill a CO2 once in a lifetime, and then your car is will be running all the lifetime. Is that possible? It looks crazy, right? But if you look at the science, then it is possible. And I will show you some examples, at least at a lab scale, that it is possible. The concept is like this. You have CO2 filled in your tank, then you have a catalytic reactor in your car. That catalytic reactor, you can name is a catalytic reactor, artificial trees, or nanomaterials. These are all just named to excite you guys. It's a material which has the catalytic properties, which activates the CO2, harvests the solar energy, absorbs the water, split the water into protons. So you take a proton from the water, and then you convert the photon into electron using the catalyst, and then you use this proton-assisted electron transfer reaction to convert CO2 into methane or methanol. Methane is my choice because it's gas. It's a CNG, right? CNG is nothing but a 98% of methane. So you filled CO2 in the tank, you converted that into methane. So now you indirectly filled your tank with the methane, right? And then you burn the methane, get the energy, drive your car, right? In this case, it's a car. You can drive any engine by using that energy. And by burning the methane to get the energy, you also produce the CO2. Now here is the trick. Now this CO2 should not go into the environment, but that CO2 again should go back to a catalytic reactor, a cyclic process. It's called a cyclic economy, where you send back that CO2 again to the catalyst, and it will again convert back to methane. And if this is possible, then you can run your car with CO2. What you need is a light, sunlight, which is free. What you need is the water, which is again available. What you only need is a catalyst. And if you can develop a catalytic system, a nanomaterial, then this should be possible. So I will try to show you some example, what we did in our lab. So how do I design these catalysts, which has so much of these ability to, activate the CO2, split the water, harvest the solar energy, so many activities these nanomaterials has to do to achieve this particular reaction. So there is a concept called nanoscience or nanotechnology, which you can say a branch of chemistry or a branch of physics. Nowadays, you must have understand now that the research is such that it is not, confined to one subject area. So nanoscience is one of that, which is a mixture of chemistry and physics, I would say. This is more a material science that we call. So what is nanoscale or a nanoscience is to investigate the properties of a matter, which is in the range of 1 to 100 nanometer. And nanotechnology is again technology built by these nanoscale materials. That's for nanotechnology. Now one may ask the question that why the scale is 1 to 100 nanometer? Why you fix the scale to 100 nanometer? Why not 101 nanometer or 1110 nanometer, 200 nanometer? So this is a very bookish definition of a nanoscience, which I personally don't believe. This is okay to really start understanding the nanoscience, but defining the nanoscience based on the nanoscale is not really a correct idea, because I can give you the material with 200 nanometer, even 1000 nanometer, which has a property, dramatically different property than their bulk counterpart. So the way we should define the nanoscience is a science of a material in which the properties of these material dramatically changes by simply changing the size of those nanoparticles. And those sizes can vary from 1 nanometer to up to 1,000 nanometer. So that should be the correct definition. Now the question is why nanoscience is so important. It's just a scale, right? You have a kilometer, centimeter, nanometer. It's just a reduction of the scale. But then how come suddenly when you go to the nanoscale, the property dramatically changes? And one of the reasons is the scale that we're talking about is extremely small. You can see how much reduction in the size we have to do to get a nanoscale. We all know about these biological cells. We think they are very small, but ideally they are thousands of nanometers. DNA is 2.5 nanometers. If you take 10 atoms and horizontally arrange them, then that becomes 1 nanometer approximation. So that's the very small scale that we're talking about. Right then, okay, so they are extremely small. So what happens? What happens to when you go to the nanoscale? So this shows unusual property. For example, the gold. Most of us use the gold jewelry, and they are very shiny yellow color. Why they are shiny yellow color? Because you have this electron cloud on this metallic gold surface, which reflects the light, and only some portion of the blue light they absorb. That's why they have this yellow color. When you convert these black gold into small nanoparticles of the gold, you see now the nano golds started showing different colors. What happens at the nanoscale is the electron cloud that was reflecting the light now becomes so mobile that it doesn't reflect the light, but it starts oscillating by interacting with the electric field. And at one particular wavelength, it absorbs that light, that particular light photons, and that gives you different colors, right? So that's called the surface plasmon resonance. And you can see now a dramatic change in the properties of the material, in this case, the optical properties of the material when you go to the nanoscale. Another example again is the melting point, right? Melting point of the gold again is 1064 degrees Celsius, really high. But if you make nano gold, gold of a 2.5 nanometer size, then it will start melting at 300 degrees Celsius. Again, a significant change in the melting point. Now, why that is happening? If you look at the melting point in a very rude way, it is just moving the atom away from some sort of increase in the bond distances between the atom, so that they go into the liquid phase from the solid phase. Now, if you look at the atoms so these are the atoms. So I'm just showing the surface of the gold. So if you see this particular atom, this is surrounded by around 7 atoms, right? So it has a coordination number of 7. Whereas when you see this particular atom or any of the atom on the surface, they have less coordination number, only 3 atoms. This atom, I need to break the interaction only with the 3 atoms, right? Or I need to break those 3 bonds. Whereas to move this atom, I need to provide more energy, more breaking of the bond. So that's why if you have more and more atoms on the surface, obviously you will need lower and lower energy to move them away, and that's the energy required to melt the gold. So because you go to the nanoscale, you have now more number of atoms on the surface as compared to the bulk, and that allows you to reduce the melting point of the nanoparticles. Right, and another thing that changes is the strength, tensile strength. We think stainless steel is the strongest. We use it for most of the building construction, but you see the carbon nanotubes. They are lighter and they are stronger, and that's why nowadays most of us are also using these helmets, which is made up of a carbon fiber with a better strength than the steel, and still a lightweight. Why they show unusual properties? As I said, why they show unusual properties? As I said, why they show how you can see now material will have 2 things: a surface and a bulk. And if you see at the scale that we are living, the scale that you see, the bulk scale material, most of the thing is in the bulk, and only small portion of that material is on the surface. Whereas if you look at these cube, if I have a 1 centimeter by 1 centimeter cube, the total surface area is 6 centimeters square. If I reduce the size of the cube from 1 centimeter to 1 millimeter, then the total surface area is 60 centimeters square. There is an increase in the surface area, but not that dramatic. However, if you change the 1 mm cube to 1 nanometer cube, you see a dramatic increase in the surface area, a huge surface area. And so that's the first thing. So you have a huge surface area when you go to the nanoscale. Now, because of the high surface area, number of atoms on the surfaces are more, and these are the atoms which has dangling bonds, which has less coordination now. So they have unoccupied orbitals on the surfaces, and these dangling bonds makes them reactive, provides them very high surface energy, and because of that, then they start reacting with different molecules or whatever they come in contact with, and that increases the reactivity of these nanomaterials. There's also concept of quantum confinement, which I will skip for now. So now, how do I build them? They are so small that how do I build them? So there are two ways to synthesize these nanomaterials. First, you take the gold ring that you are wearing and break it down until you get a nanoscience particles. But as you can imagine, that will be really difficult, right? How do I break down to a nanoscale? There are some laser techniques which allows you to really go to the nanoscale from the bulk scale, but then there is a limitation on the control. You don't get a monodispersed particle size. You cannot have a shaped nanoparticles, which is needed to tune the properties of these materials. There's one more technique which is in generally used, which is called the bottom-up approach, where you start from a basic molecule, ideally an atom. You start from the atom and build the nanoparticles. Obviously, you don't have the atoms as a source, so what you do, you take a salt, some salt. Say if I have to make a gold nanoparticles, then I use some gold salt, gold chloride, and then I reduce the gold chloride to gold atoms. Now I have my, in a conical flask, I have the solution of gold atoms, and I keep increasing the concentration of those gold atoms so that it reaches the supersaturation. And now to minimize the total energy of the system, these gold atoms meet together and form, the seed or form the nanoparticles. So by controlling the temperature, concentration, the way you add, you can then control the size of the nanoparticle, you can control the shape of the nanoparticle, you control the morphology of the nanoparticles. And that all allow you to tune the properties of these nanoparticles that is needed now to build the so-called artificial trees to capture and convert the CO2. Okay, another question quickly is how do I see them? So you cannot use optical microscopy to see the nanoparticles because nanoparticles are smaller than the wavelength of the light, visible light that you have. So what we generally use is electron microscopy. You use electron beam as a light source and you expose your sample, your nanoparticle with electron beam, and then there's a technique of transmission electron microscopy and scanning electron microscopy, which study how these electrons are interacting with these nanoparticles, and that gives you the image that really gives you the picture of those nanoparticles. So these are the TEM, and these are how the TEM looks like. So that allows you to that provides you the information about particle size, shape, whether they are monodispersed. You can also go to the atomic scale resolution and find out how the atoms are arranged within those nanoparticles, whether if they are crystalline or amorphous. These are the SEM images, which was discovered in 1981. These are ideally nanoparticles, but they are so small, around 4 nanometer. They look like a dot. So you call them dot and quantum because these materials has this very strong quantum confinement effect, and that's why we call them a quantum dots. And by tuning their sizes and the core and shell material, you can get a light emission of a different wavelength. So very basic discovery, very fundamental research discovery, which is now being used as a quantum dot LED TV, right? QLED TV, several of you may already have it, right? A very high resolution TV, which is based on the quantum dots. Another example is carbon nanotube, discovered in 1991, one of the very strong and conducting material. And now carbon nanotube is used in different places, flash memory, lithium-ion batteries, even in concrete. So you can see how the fundamental research can help us to develop different technologies. And this is all ideally the chemists who did all of these things. Graphene, conducting material, a flexible conducting material. So you can, design the flexible electronics using these graphenes. Most of our air is now getting polluted. So, the TiO2 is a semiconducting material having the ability to harvest the solar photon and create the electrons, which can be used to, degrade these pollutant in the environment. So you can ideally paint your walls of your home and different buildings, and that should ideally, purify the air around it. So you can see direct use of nanoparticles, nanomaterials in our daily life. Now we'll come back to our main topic, which is about role of chemists to stop the climate change. So I told you the one of the simple way, although one of the most challenging ways, is to capture and convert the CO2. We know trees do that, but mimicking the nature is not that easy. So we need to find out a way, design artificial trees, which is nothing but a nanomaterial, which will do the same thing what trees are doing, capturing the CO2, harvesting the solar light, splitting the water to give you the proton, and then again converting the photon to the electron. And so you have proton, electron, and the CO2, which gives you methane, methanol, ethanol, different fuels and different chemicals. So this I already discussed. So how do I design this catalyst now? And this is what we do in our lab. So now the talk could be a bit of technical. I'm going to give you some examples how we did that in our lab. So this is our hypothesis. This is the way we design the catalyst. So we, rather than using a very small nanoparticles, I showed you like 5 nanometer gold. They have a very high surface energy, surface area. They're very active, very reactive. But if you use them as such, then they try to agglomerate. They try to aggregate, sinter together, and the stability is the serious issue of these nanoparticles. What we do, we take these nanoparticles and fix on some support. Now, since you are fixing on a support, then they don't move and they don't meet and they stay away from each other. And that keeps their activity intact for a longer time. So what you need is an active site. Active site is the site which activates the CO2, activates the water, activates the hydrogen gas to react with the CO2. So that's why we call them the active site. Now, support is a material on which these active sites can be supported, right? So what I need is a high surface area material so that I can support lots of these active sites. Then I also need my material to harvest the solar energy, to capture the solar photons and then transfer that solar photon into, say, electrons or heat, and see whether one can use those electrons and thermal energy to carry out this reaction of CO2 plus hydrogen to get you methane and methanol. So first thing, we need a catalyst support. So in our lab, we developed this support. This is called dendritic fibrous nanosilica. This is ideally a sand on the beach, but sand at a nanoscale. Scale is 50 nanometer to 1200 nanometer. I get 50 to 100, 100 to 200 different sizes based on the need. And they have this dendritic fibrous morphology, and that's why we call them dendritic fibrous nanosilica, DFNS. They have excellent surface area, 500 to 1200 meters square per gram. 500 meters square gram is like if you take a 1 gram powder of this nanosilica in your hand, it's like a 1 football ground in your hand. So that's the high surface that you can achieve by simply taking 1 gram of material. Then they have several inherent properties like a thermal stability, mechanical stability. So you can do high temperature processes, high pressure processes using these materials. And the most important thing is the synthesis. This is not obviously when we discovered, we use some advanced technique to synthesize, but right now, recently we wrote this nature protocol where we showed that one can synthesize this material in any lab, which has this round bottom flask, heating mantle and the stirrer. So it's very, very easy to synthesize, and one can now synthesize in a larger scale. So these are the SEM images, scanning electron microscopy images, indicating the monodispersed nature of the particles and those fibrous nature, dendritic fibrous nature of the particles. Now the question is, why we obtain these spherical but fibrous particles? Why not a different shape? Or why not a smooth surface? Why fibrous dendritic surface? And that we try to answer that question in our lab, and that can be answered by knowing the formation mechanism of that material. So nanoparticles are sometimes very easy to synthesize, sometimes follows very complex process. In this case, we use the CTAB molecule as some sort of a template. You create a template using these salts, and within the template, you create a template by self-assembly of these micelles, these surfactants, and then within the template, you grow the silica. I will show you the animation. So these are the template molecules. Blue ball is, quaternary nitrogen, polar head, and this zigzag line is gray line is a CS2 up to 16, C16. So now these are polar, non-polar molecules. Molecule having polar and non-polar parts. So these are the surfactants. which form a lamellar phase in our case by controlling the concentration and the solvent. And then you have these another molecule, we call them a co-surfactant, which stabilizes these interfaces and form these lamellar phases. But we observe that these lamellar phases are not floating flat into the solvent, but they are in the form of a microemulsion droplet. We call them bicontinuous microemulsion droplet because we call them a mixture. They use the solvent, which is water and xylene, and the surfactant, and they're continuously mixing with each other, mingle with each other, I would say. So these droplets, these are not a nanoparticle, these are a nanoreactor or a template. And within those channels that you see, you put the silica precursor and you grow the silica in this channel. So this is like a templated synthesis. You create a template and then grow the silica in the template. So based on the shape and size and morphology of the template, you get a different silica. Then we learn to merge them together. So if they merge together, you get a bigger droplet and you get a bigger size DFNS particle, silica nanoparticle. Or we also know how to keep them away from each other. You get a smaller nanoparticle. And that's how we tune the particle size of these nanoparticles. So our material, which is invented by my group, and now we have several patents. So this is one of the Indian invented material used by researchers worldwide for a large number of applications in CO2 mitigation, which involves capture and catalysis, a conversion, other catalytic protocols, oxidation, reduction, CC coupling, CH activation, metathesis, hydrogenolysis, range of applications. Energy harvesting, energy storage in supercapacitor, sensing, and large number of applications in drug delivery because it has this open structure. You can load lots of drug molecules and create some sort of a linker to break it down by exposing with light or something and selectively deliver it to the infected part of the drug. So there are ways to deliver the drug selectively, and people have used the DFNS to achieve that. So that's the support. The next part was the active site. So active site is something which will activate the CO2, dissociate the hydrogen, and let the CO2 hydrogen react to get you the methane. Most of the time, active sites are made up of metal nanoparticles. See, this is it's not there, but the metal nanoparticles are expensive. They are highly unstable. So we wanted to find out an alternative to the metal catalyst, and the best alternative is metal free. But what could be the active site which will do the job of a metal? And then we came up with this idea of creating the defects in the material, and the defect itself then act as active site. So in our case, the defect is, when I say silica is SiO2, so we removed some of the oxygen from the SiO2 and you created two Si radicals and this oxygen vacancy where CO2 can sit. And that allowed, and then Si radical can activate the hydrogen molecule. And that allowed us to, convert CO2 to methane simply using the silica, simply using the sand on your beach ideally, obviously at the nanoscale with the defects, right? So this is one of the example. Maybe I skip the technical details. And then only drawback of this particular process, this is the typical reactor that we use. We mix CO2 plus hydrogen, pass through the catalytic reactor, which is heated at 400 degrees Celsius, and the products were monitored by the gas chromatography. The only drawback here is that I need 400 degrees Celsius. So this is energetically heavy process. So now either I do a reaction at a lower temperature, which was not possible, or I get that 400 degrees Celsius from the sunlight. So that's the second project where we wanted to get us capture the sunlight and convert that sunlight into a thermal energy and use that thermal energy. And then we came up with the concept of cold heating. So obviously, at first this looks wrong, right? How can something be cold and heated? But the concept is this. When I say I'm doing the reaction at a 400 degrees Celsius, ideally I need that 400 degrees Celsius to overcome the activation energy barrier. And that is happening only at the active site, right? In this case, the defect sites. So, but to get that 400 degrees Celsius at the active site, what we do is we heat entire reactor, right? But that's how we heat the system. But in reality, I don't need to heat entire reactor if I somehow can create 400 degrees Celsius only at the active site, localized heating. So can I keep my reactor, say, at a room temperature, but generate the heat only at the surface of the active site? That's the question. And that will make this true. That will make the cold heating concept true. And that's what we did. We created a black gold. We synthesized, we took these DFNS and then coated these with these gold nanoparticles. And there we tuned the distances between the gold nanoparticle. We brought them together as close as possible so that the electron cloud of these gold nanoparticles start interacting with each other, start coupling with each other. And that allowed us to then harvest the total solar energy. You can see now you can harvest entire visible and near IR light using these black gold material. So you can see the gold becomes black now because of these interparticle plasmonic coupling and the particle size effect. So black gold is a gold, metallic gold, zero oxidation state, no doping, no functionalization. Still it is black because it has now ability to harvest most of the sunlight. And that's why it's black. Now, once it absorbs those photons, material has to do something, right? It has now excess of energy. So what they do, this energy damping is being used to either excite the electron from the Fermi level of the gold to the excited state. We call them the excited electrons or hot electrons, which you can use, which you can transport to the CO2 molecule, make the CO2 molecule now reactive. I told you, right? CO2 is a linear molecule, very difficult to react. That's why it is very stable. And that's why the CO2 chemistry becomes so challenging. But if I inject the electron into the CO2 molecule, it gets a CO2 radical anion and it's really reactive now. Then you can add the proton or hydrogen or some other molecule and you get different chemicals out of that. So that's the one way. You create a hot electron, transfer it to CO2 and convert that to methane, a fuel. Or if the lifetime of these excited electrons is so short that they come back, so when they relax, they collide with the atoms, the vibrating atoms. We call them the phonon. And because of this electron-phonon coupling, all that energy that was absorbed, the photon energy converted to heat, and you produce lots of heat. You generate lots of heat at the surface of these black gold. And you can see this is how the gold looks like, and this is how the black gold looks like. And now, by using the heat, one can then use a simple science. You can you take a glass with the water, add the black gold, expose to the sunlight, black gold capture all the sunlight, convert that solar photon into heat, and then that heat evaporates the water vapor. And then you condense the water vapor. So you can ideally convert seawater into drinkable water by simply putting the black gold. You may think of, oh, gold is so expensive. Why do I use the black? Why do I use the gold? Can I use some other element? Ideally, yes. But we're trying different element, but this seems to be the most active and most stable, right? You can use aluminium instead of gold or a copper out, but they're not stable. They oxidize this and then their activity goes down, whereas gold is active and stable. And these are the catalytic process. That means once I have the black gold, I should be able to use it for thousands and thousands of times. It's recyclable, reusable. So that makes the process sustainable if the productivity is higher. And this is our result. See, CO2 plus water, right? And DPCCX is the black gold. Visible near IR is the sunlight. You get a methane, right? I showed you this thing, big dream, running your car lifetime, just filling the CO2 only once. And you can see now, you take that CO2 and you have this catalyst, you need this catalyst, and this black gold has the ability to harvest the solar light, split the water to get you methane. And this dream can be true. Now, the negative side of it is, although this is a very exciting result, but you look at the y-axis, the methane yield, this is just a 1.5 micromole per gram, which is extremely small. So at as a fundamental discovery, this is a good to start with, but the values on the y-axis is really low, really low. So one has to improve these to make this dream come true. And that's what we are trying to do in our lab, somehow trying to increase the activity of the catalyst to produce more and more methane in terms of productivity as well as in terms of kinetics, because you need to do that very fast. Okay, in another 2 minutes, completely different topic, but I think it's another important topic, which is the waste plastic, right? This is how it is in our country. It's everywhere. It's lying everywhere. Maybe Mumbai is more cleaner, but if you go to other cities in the country, and in Maharashtra, you will see plastic everywhere. And we did this, right? We bring the plastic, we throw it away. We don't have the concept of reuse because they are cheap, right? So you throw it away. Plastic is not only lying on the surface of the planet, but it is also in the air. There is a very recent paper in Science 2020, which named it as a plastic rain, which is more dangerous than the acid rain. So these microplastics are floating in the air, and when you have a rain, all of that microplastic become part of your water body. And then plastic goes into the water, and those plastic is eaten by the fish, and fish, you eat the fish, we eat the fish, and the plastic is already part of our body. So it's really serious issue. How do I solve? There are several ways. One is, the best way is to reuse. Ban the plastic. Make sure that we always reuse the plastic. And in terms of the chemistry, in terms of the role of a chemist to tackle the plastic waste problem, the simple solution is, can I degrade all the plastic waste back to the chemicals from which it is produced? These are all polymers. So can I get the monomers, alkanes and alkenes from that? So ideally, yes, the chemistry allows you to do that. You can degrade the plastic into the basic chemicals, but the energy required for this process is extremely high. So to break down the 10 rupees bottle, I cannot put 100 rupees of energy, right? So that no one will do that. So energetically, it's not sustainable. Economically, it's not sustainable. So somehow I need to reduce the temperature required to degrade these plastic back to the chemicals. And if that is happened by the catalytic process, then this could be also feasible. So that's what we recently, now in order to do that, in order to reduce the degradation temperature of the plastic, you need to use some sort of acid catalyzed degradation, acid catalyzed CC bond breaking, and solid acid, like these are the solid material having acidic properties, are known to be the best. And but the material reported in the literature, they were strongly acidic, but the pore size of these solids are so small that the plastic cannot really go in, cannot diffuse in, and therefore they cannot degrade. So we wanted to have a solid acid which has a bigger pores, bigger holes, so that the bigger polymer molecule can diffuse in, and stronger acidity. And that's the material that we recently developed. We call them acidic aluminosilicate, which has a mesopores and acidity like a zeolites. And that allowed us to then degrade the plastic to the chemicals. We were able to reduce the degradation temperature from, say, 450 to around 350 degrees Celsius, 100-degree decrease in the temperature, which is again at a research level a good start. But again, this is not what is required to make the process sustainable. So you need to really degrade the plastic at less than 100 degrees Celsius. You need to really develop a catalyst which is stable, reusable, and so that you can degrade the plastic even less than 100 degrees Celsius. And if one can do that, again, the plastic problem, one can contribute to the waste plastic problem. Chemists can contribute to the waste plastic problem. And you must have seen now, either it's the CO2 conversion increase in the efficiency or the plastic degradation. It is the design of those nanomaterials. It is the design of the materials. And this is all about the synthetic chemistry. This is all about the chemistry, how I tune the properties of the material, which element I use, how I connect them, what is the oxidation state of these elements, how they are bonded, right? What is the morphology, what is the surface area? All of these aspects we need to think, we need to hypothesize, we need to come up with different materials design, and then synthesize using the chemicals that is available easily, using the reactors and chemical processes that can be reproducible and can be upscalable. And this is what we are trying to do in our lab. Okay, with that, I'd like to conclude that nanochemistry can help us to tackle the challenges of energy and environment and protect us from the climate change. I'd like to thank my group who did this work. And I also like to thank Department of Atomic Energy, which give us majority of the funding, then Indo-French CEPIPRA, BASF, Shell Industries for funding, and then recently Mission Innovation, DST India funding. With that, I'd like to thank you all for listening to me, and I'm more than happy to answer the questions.
Hello. Yes, everybody will be open to accepting questions now. The question answer session is on. You can feel free to unmute and ask, or you can also put it in the chat box.
How do we see AI in nanochemistry? Yeah, so there are several use of these computational chemistry and artificial intelligence to mine the data that is available in terms of the synthesis and catalysis and come up with a new catalytic design. Although I'm not sure how much it will really help, because even after knowing all the chemistry and the physics of these materials, it's very difficult to design the material from start. We always first try different materials, and based on the learning of those materials, we then design the material. But there are groups now who are trying to use the AI to design the new materials, new catalysts. Gold foils are used in foods. They are in nanometer range. Will they agglomerate and cause problems to humans? Are we using gold? No. If you're seeing them by eyes, I don't think the gold foils are in nanometer range. They must be in a micron size at least. Will they agglomerate and cause the problems to humans? So that is another issue with most of the nanomaterials, the health safety, what happens to them when they enter into our system, our body system. That is something still a research topic. Several groups are working on that, and that one has to really worry about. The way it happens is, if I develop a nano catalyst, then I have to do some sort of a life cycle assessment. I do the LCA, I find out where that catalyst will end. Most of the time catalyst is reused, and also in terms of the health aspect of those nanoparticles. Can black gold be used for thermostic applications? What is that? Are you talking about these thermal applications where you deliver these gold, a nanoparticle at infected part and create a thermal energy by exposing with light and kill that some sort of say cancerous cell or something like that? So that is something people are already using, the black gold to create the localized thermal heating of the cancerous cells or something like that. As these proposed nanomaterials always need sunlight, where these materials can be used most of the times. True, this will be used. These nanocatalysts can only be active during the daytime when there is a light. We are also trying to develop a catalyst which doesn't need a light, which then need a heat energy, right? So it's like you convert the solar energy into electric energy, and then electric energy can be used to generate the heat, and then you use that heat to carry out the CO2 conversion. So one has to think about some sort of a hybrid system to use these materials in reality, in real applications. What kind of platform do we use to assemble molecules to nanoscale by the bottom-up method? We don't use any platform as such. Most of these chemistry can happen in a simple round bottom flask or a conical flask. So we choose a molecule which has a tendency to self-assemble. These are the natural tendency to minimize the total energy of this. If you take a surfactant molecule, you form a normal micelles or a reverse micelles, or you tune the concentration of them to form a lamellar phases, and that generates the template. And that is a template which you can use to prepare nanoparticles. Along with plastic, there is also excessive buildup of biomedical waste. Can nanotechnology be applied for curbing this? Ideally, could be if these biomedical waste is also need a heat. Then again, you can use these black gold to capture the sunlight and produce the heat and use that heat to degrade these biomedical waste. Again, the question is how economically feasible these processes are, which is at the current stage of research. None of these processes are economically sustainable, but that's where the research is needed. That's where fundamental research is needed. That's where the engineering design of different reactors is needed. How big can the role of a membranes be seen in the industrial application of carbon capture and utilization? Yeah, membrane can play. Membranes are playing a very important role. So if you can capture the CO2, or you develop a sorbent material which is in the form of a membrane, then the handling of those sorbent will be more efficient. If there is a mixture of gases, CO2 plus a hydrogen plus some other gases, then membrane can selectively trap one gas over the other gas. So there are several applications of the membranes in carbon capture and specifically even in a utilization. Also, you need to separate somehow. If you produce methane and hydrogen by reacting with CO2 and water, then if you want to separate the CO2 and hydrogen, membrane technology could be one of the best way to separate them. Will there be picochemistry in the future? I don't know. I don't know. How do I make it? You never know. I don't know. You see, we are already at the atomic scale, right? Can I go below atom to make a material? May not be, right? So I think we're already at the bottom. But yes, how is the paints be used to trap pollution? Uh, Paints, maybe you put a sorbent, CO2 sorbent material in the paint and paint the wall, right? And then those sorbent, which is part of your paint, can capture the CO2. In terms of air pollution, I already showed you one example of the TiO2, which is a part of the paint, and TiO2 has the ability to harvest the light, mainly the UV part of the sunlight. And once they absorb these UV photon, you created these excited electrons. And this electrons is highly reactive. It can, react with water to produce the OH radical, which can then degrade all the organic pollutant that surface that paint come in contact with. Is it possible to carry out CO2 hydrogenation reaction without using active metal, simply by creating a defect in the support material? No, that's the paper that I showed you, right? So this is for the first time we showed that this is possible. That's our PNAS paper, where we showed that one can create defects in the silica material and do the CO2 hydrogenation without using any active metal, where the metal job is done by the defect side. For CO2 reduction, is design of a setup is also important to increase the concentration of a product. Yes, the reactor design is extremely important. Whenever we develop a material, we also do a reactor design in the lab, but obviously all of our work is at a very small scale, right? We do a catalysis in a milligram scale. Our reactors are all very small, but how you prepare the catalyst bed and how you flow the gas, how you expose the sunlight, all of these really impact the catalytic activity as well as the selectivity. So reactor design is extremely important, and that is where the things are missing in India. The fundamental researcher don't talk with the chemical engineer or instrumental engineer. If they talk with each other, maybe parallelly one can come up with a material and the reactor and develop the process, right? That's what the Atmanirbhar Bharat wants us to do. The coming decade is considered to be the most important for mitigating the CO2. Is there any current scalable technology under development right now? Obviously not in India. The way things work in India is until the people in the West do it, we don't do it. That's an unfortunate way we think. Obviously, there's a push from the government now that we should do it, and we can do it, but I don't think there is anything in India. But there are several CO2 methanation technology in the European countries where they are trying to use the excess electric energy and use the electric energy to generate the heat, and then they are reacting CO2 with a hydrogen. You can use the electric energy to split the water to produce hydrogen and do a catalysis to get you the methane, which is your CHG. And there are several other processes. There are several other technologies that people are trying to develop.
Aren't we in most of the countries? Aren't we still using coal to make electricity? So you're using coal to make electricity, and you're using electricity to cut down the carbon. So isn't it just a cycle again?
Yeah, no, that's a very bad idea. Yeah, we should not do that. But now, because of the excellent development of a solar energy, solar cells, where you can convert the solar energy into electricity, right? All the solar panels that we see all around. So there you don't really need to use the coal to generate the electricity. Obviously, if you are burning the coal, generating the electricity, and again then capturing the CO2, it has no meaning, right? It's just a wastage of our energy. So I'm talking about the excess of electric energy coming from the solar panels. Are the nanofabrication techniques like a photolithography or vapor deposition scalable currently? Although we don't use it, but I think there are nowadays a technique which allows you to upscale the vapor deposition and photolithography, even the atomic ALDs. So, but again, the way I think at least the solution phase synthesis is more sustainable, upscalable, and with a better control as compared to any of these instrumental techniques. How feasible is the paint technology? Would the frequency of repainting increases with this? Uh, Ideally, yes. If your TiO2 is getting deactivated because of the dust or something like that, you may have to repaint or may have to wash it and deactivate. So I just gave one of the example, right? The one has to think several other possible ways to, purify the air by these nanoparticles. This is a very interesting question. Is the funding sufficient in India, private versus government, to mitigate the effects of climate change? Yes, you need more and more funding. You need a high-end instrument. But I think the problem in India is not about the funding. We should get more and more funding. I should not say that. But I think it's the how you utilize the funding, which is the key. And there we lack like anything. We have lots of institute and lots of group get large amount of money. They buy very high-end instrument. But if you look at the output, forget about output. If you even look, so for example, for research in nanoscience, you need a transmission electron microscopy, a high-end transmission electron microscopy, which allows you to see atoms, their arrangement, and how they behave when they interact with CO2. Now, my own institute has a Titan TEM, which costs you around 40-50 crore rupees and around 1 crore rupees of maintenance. But from last 2 years, I was not able to do one simple sample analysis. So this is not about the money, I guess, right? So you already have the money, you already have the facility, but it's about the way the science is administrated in this country is the problem, right? So there is no some sort of a control or monitoring about use of funds in this country, and that's why we all struggle. Okay, maybe that becomes more a political answer, but that's the reality. Sir, where can we use nano encapsulation? How far it is feasible? A nano encapsulation, I don't understand. What do you mean by that? Are you trying to encapsulate? So one of the things people do in drug delivery is they take a nanoparticles and then load the drug in the pores, right? And your drug get encapsulated in that nanoparticles, and then they use it to deliver at a specific point, and then the delivery becomes more efficient, and you can use small concentration of drug and release that at that particular point. So people are using some sort of a nano encapsulation in drug delivery. What are the current source of easily portable and high energy density power sources? Hydrogen. So hydrogen now, in fact, in recent budget, there is this hydrogen mission, right? But hydrogen is ideally an excellent energy source because the product that you will get after using the hydrogen will be in the water, so there's no pollution. But the problem with hydrogen is the storage. You need a high pressure reactor to store the hydrogen. So if you want to drive a car, you need to have another car to store the hydrogen. Obviously, there are a technology now to find out a way to store the hydrogen at a room temperature at atmospheric pressure, either using some porous material or converting hydrogen to, again, formic acid or a methane. So one of the way to think about converting CO2 to methane is I react CO2 with hydrogen, which you produce from the electricity, electricity coming from the sunlight. So now what you solve two problems. You solve the storage of hydrogen. At the same time, you solve the problem of CO2 in the environment, and you convert that into the methane, and then you burn the methane. Right. So that was the last question, I guess. So yes.
I would like to request everyone to turn on their videos so that we can capture this moment. Safe cheese, you're all on camera. So there's one more question in the chat box after the photography session gets over.
Yes, small industries group tend to find easier way to accept the government law. How can we try to make them on site to reduce the pollution without much government interference? Yeah, it's not only small industry, all of the industries, they find the easier way. Their objective is to, earn the money as much as they can. And what other countries did, which India never did even today, is the something called a CO2 tax. So if you produce the CO2, you pay the tax to the government, right? And either you capture the CO2 then and use that CO2 for something else, then you don't need to pay the tax. And if you are releasing the CO2, then you pay the tax, and you can use that money, government can use that money to develop the technology and again capture the CO2. So without government bringing the CO2 tax, none of the science that I spoke today, either the CO2 capture or conversion will ever be, see the real application. Because all of these technology needs expensive materials, expensive catalysts. But it is not the climate change is all not about the money, right? It's about the saving the planet. So you need to force the industry to pay the taxes, right? Pay the fine to generate the CO2. And that's what several other countries have already done, the CO2 tax, which this country is still waiting for. The titanium nitride has a broader plasmonic resonance at the optical absorbance law, and optical is larger than the AU or AG. So why you have not chosen? That's a good suggestion. We are trying different materials, and we can even think about TIM. Please remember, when we have to develop a photocatalyst, it's not only about light absorption. I think we showed you that okay, it's the black gold, it absorbs entire visible and IR light. But when I showed you the photocatalytic activity, it was very low, right? So that means there is not only a direct relationship between the light absorption and catalytic activity. There are several other parameters that plays the role. In this particular case of a photocatalyst, how the electrons and holes are separated. What is the lifetime of that electron? That decides the photocatalytic activity. If the lifetime of the electron is high, then the electron goes to the CO2. Otherwise, it comes back and meets the hole, right? And then you cannot use the electron. So we're trying to do some sort of a hybrid system where as soon as the electron is formed, it goes to some other material and hole is in some other material. And that way you increase the lifetime of the electron and then you transfer that to the CO2. Yeah, how feasible is the idea of hydrogen economy? There are deep debates, right? So some people say this will never be feasible, and some people say this is the way to go ahead. I really don't know. Obviously, the water splitting doesn't seem to be an efficient process to generate the hydrogen, but electrochemical water splitting seems to be the best way to generate the hydrogen, a cheaper way. Most of the hydrogen gas that we use in our lab is using these electric hydrogen generator, where you can generate lots of hydrogen. But the challenge here is the storage of the hydrogen. If one can come up with a material which can store the hydrogen at room temperature without any energy at atmospheric pressure, then hydrogen economy may work, right? So it's all about how the research and technology develop in coming days. That will decide about the hydrogen economy and methane economy, all these methanol economy, all of these economies. Okay, that was the last one, I guess.
No more questions? I can wait for it. Okay. An investment in knowledge pays the best interest. On behalf of the entire Vortex team, I would like to take this opportunity to thank Professor Vivek Polshettiwar for conducting this informative and inspiring lecture. Thank you, sir, for your insights into chemistry and climate. It was an honor to have you here and to be a part of Masterclass. I would also like, yes, sir. I would also like to thank Professor Vandana Patrawal and Professor Kharkar for sharing their valuable time with us. A huge shout out to the amazing audience as well. Thank you all for helping us make this event a success.
Okay, bye-bye everyone.
Thank you so much, sir.
Thank you.
Sir.